First of all, when do we use op-amps? We use the operational amplifier when we want to perform analog signal processing. For instance, if we have two signals, two voltages that we want to sum, then we can use operational amplifiers to calculate the summation of these analog voltages, these analog signals. Or we can take the difference between two signals using op-amps. Another application is, for instance, taking the integral of a signal, taking the integral as a function of time, for instance. Similarly, taking the time derivative of a signal, it can be done with op-amps. And of course, other functions of the op-amps are just like the amplification, the signal amplification in a very clean and nice manner. Okay, first of all, I want to investigate the following circuit. So I have an input like this, in, and here is my output. So what happens in this circuit? First of all, I know that there is negative feedback here, because when the input is positive, then the output will be negative, and it's going to feed this back to the circuit, back to the input of the operational amplifier. And I can use the rules for the closed loop operation in an op-amp. In this case, positive and the negative terminal should have the same value, so negative terminal is Vin. And since it is connected by the same wire to the output, I conclude that the output is equal to the input. And such circuits, such functions are called buffers. It's basically a buffer implemented by an operational amplifier. Now you might ask, well, what's the function of this buffer? What good is this buffer? So, because I'm having the same input voltage and the same output voltage, right? So it looks as if there is no function being performed on the signal. Now the answer is that the input can be a very weak signal. Now when we think about signals, think about the power that's contained in a signal. And power for electrical energy is the voltage times the current. For instance, this input voltage might be coming from a microcontroller, and it might have just only very small amount of maximum current possible. But let's say we want to drive a motor by using this input voltage at the same input voltage level, but since the microcontroller cannot give out a large current, I cannot drive a motor directly with this signal. What can I do in this case? I can make this signal stronger by increasing the maximum amount of current that can be drawn from the circuit. In this case, of course, I don't want to change the voltage level, because let's say the motor is running at a certain voltage, but I want to be able to provide a larger amount of current to the motor. Now in this case, I can use this buffer circuit so that a weak signal, a signal which has some voltage level but a low amount of possible current, it can feed into my operational amplifier, and the operational amplifier will produce me an output voltage that has the same value with the input, but the thing is the maximum possible current that can be drawn from the op-amp circuit is much larger than the input signal. So the buffer basically makes the signal stronger, not by changing the voltage, but by allowing a larger amount of current to be provided to external circuitry. Let's look at the following circuit. In this case, I have an op-amp, and I have my output, a feedback resistor here, and I have two voltages, V1 and V2, and two resistors, R1 and R2, connected to the negative input like this. What happens in this case? Okay, so let's apply the rules for the op-amp. So first of all, positive terminal is at 0 volts, so negative terminal should be at 0 volts as well. And I know that there is no current flowing into the op-amp. So what happens is a current will flow like this, I1, and another current will flow like this, I2. Now I2 or I1 will not flow into the op-amp, so I2 will come here. And the summation I1 plus I2 should flow through the feedback resistor. From here I can write the Ohm's law for each of these three resistors. So first of all I can write, for instance, the value of the first current is, so it is basically connected between V1 and 0. Here is V1 volts, right? And here is 0 volts, because remember, like here is 0 volts, here is 0 volts, etc. So the difference, the voltage difference across R1 is V1 minus 0. And of course the resistance value is R1. So I conclude this is V1 over R1. Similarly, if I look at R2, I see that it is connected a voltage difference between V2 to 0 volts. So the current that's flowing through the second resistor is between V2 minus 0 over R2. So it's going to be V2 over R2. Okay, how about the current that is flowing over RF? So basically I can call this current as IF, and I know that it is the summation of I1 plus I2. But this current is also determined by the voltage differences between this point and the other point, so across the resistor. So on the left hand side, it is connected to the 0 volts, right, because of the negative terminal of the op-amp. And on the right hand side, it is connected to the output voltage V out. Now in my convention, I took the current flowing from left to right. So I should be consistent. So basically the voltage difference from left to right is 0 volts minus V out. Now I am calculating IF over the resistance itself, so RF. So it is basically minus V out over RF. Now I can combine these three equations, so I1, I2, and IF, by using the summation formula here. And if I do this, so I can write IF is I1 plus I2, and IF is minus V out over RF, and I1 is V1 over R1 plus V2 over R2. So from here I can conclude that the output voltage is minus 1 over, the output voltage is minus RF over R1 times V1 minus RF over R2 times V2. And as you can see in this case, by changing the values of RF, R1 and R2, I can have different coefficient in front of V1 and in front of V2. So the utility, the function of the circuit is to calculate a weighted sum of V1 and V2. Output is basically a weighted sum of V1 and V2. Of course, it comes with a negative sign, but I can use an inverting amplifier, for instance, right after this circuit to get the sign as positive as well. Instead of a negative sign, I can get a positive sign. For instance, in this particular example, if I choose R1 equals R2 and it is equal to RF, then I will have V out is simply minus V1 plus V2. And again, if I use an inverting amplifier with equal resistances, I will then obtain V out equals V1 plus V2. And of course, this is just a simple summation in this particular case, but I can obtain any linear summation between V1 and V2 by using this circuitry. Now, if I had 10 such voltages, I could have just put them in parallel. For instance, let's say I have a V3 here. I can just easily connect it to this circuitry from the same point, and it will be another factor in my formula. Let's see what happens in this circuitry. In this case, I have an op-amp. It is connected to the ground at the positive terminal. It has the input voltage here and the output voltage here. With input voltage, I have just a regular resistance, but between the input to the output, I have a capacitor as the feedback element. Now, this is a very interesting circuit. And let's just apply the rules of op-amp to this circuit. So first of all, positive terminal is at 0, so negative terminal is at 0 volts as well, so 0 volts. And I know that no current will be flowing into the op-amp. So the input current, so let's say I1, is equal to the current that's flowing through the capacitor, I2. Now, I know what I1 is. I1 is simply, so it's V in to 0 volts, so V in over R1. So what is I2? Now I2 flows over the capacitor. Let me remember the basic equation for the capacitor. Now in capacitor, charge is stored, so there is a charge like this, Q, like plus, plus, minus, minus, etc. And the charge is basically is equal to the capacitance times the voltage difference between the capacitor. So the charge on the capacitor is C times, now the voltage difference is between, in this case, 0 volts to the minus V out, so it's going to be minus V out. So the charge is minus C times V out. Okay, so this is just the charge on the capacitor, but I was trying to get a relationship for the current through the capacitor. Now, what is current? Current is basically the current can be calculated by looking at the time change on the charge on the capacitor plate. Why? Because if current is flowing, it means that the charge is basically moving from the capacitor and into the circuit. Right? So like the charge is changing on the capacitor. And this is basically the formula. And it can be written formula as the I2 is basically the time derivative of the charge. So I need to take the time derivative on this equation. So then dq by dt, which is I2, is basically minus. Now the capacitance doesn't change as a function of time, it's constant, minus, but the output voltage can change and will change, dv out by dt. Okay, so now I can combine these two equations, so for the current and current number 1 and current number 2, because I know that it has the same value, I1 should be equal to the I2. And from here I can write V in over R1 equals to minus C times dV out by dt. Now of course I'm interested in calculating the output voltage as a function of input voltage, so I can take the integral of each side, and I can write V out is minus 1 over R1 times C, and integral t starts from 0 to, let me use another, say, tau starts from 0 and tau goes to t, V in of tau d tau. So on the right hand side I have the integral of my input voltage, and on the left hand side it's just the output. So basically the output is calculating the integral of the input voltage. So if I want to calculate the integral of an analog signal, I can construct this circuit, and what I will have at the output is going to be the integral times a constant factor, which is 1 over RC. Now in this case, be careful that, like the integral, what is the unit of the integral? It is basically voltage times seconds, right? Because I have voltage here and time here. And I know that RC has the units of seconds, so 1 over RC has the units of 1 over seconds, and their multiplication basically makes it voltage, and left hand side is voltage as well. And this circuit is called an analog integrator. This is an integrator for using op-amps.